have seen this algebra before. Okay. So now, let me just give you an example. So the previous configuration I've showed you, you can simplify it in the following way. So you see here you have a closed loop, so you can replace it by a factor delta. This loop you have to follow it like this, and it goes like this. And this loop, again, you can straighten it, and it just becomes this. So these are all the rules in your algebra. Then the question you might want to ask is, what are the irreducible representation of this algebra? So of course I didn't mention it, but it creates you an algebra. So it's trivially it's associative, and it has all the properties of an algebra, and it just follows from the diagrammatics. And then you want to study its irreducible representations. So first observation is that this algebra is finite dimensional. So it's not obvious from what I told you, but it is finite dimensional. So there are finitely many irreducible representations, which is already quite nice. And you can classify all of them, and they're labeled by an integer j. Which goes from 0 to n over 2. And I always assume that n is even, so that it's simpler for the exposition. The description of this wj is actually very simple, so they're just given in a basis by half diagrams of your temporally algebra. And the integer j, it parameterizes the number of through lines you have in your half diagram. So let me just give you an example. For 4 lattice sides, so W0 is a module with no through lines. So you just have to draw all half diagrams which do not have any propagating through lines. So the only two choices is this and this, because loops are not allowed to intersect. And for W1, you have 2 propagating lines. So basically you don't have many choices. You either put the 2 lines to the right, or you sandwich a cut between them, or you put them to the left. And then W2 is just a trivial representation where you just have propagating lines like this. And there are some additional rules, but for this W1 and W2, but they are not very important for now. And so let me just give you the action of a template algebra on these diagrams. So for example, E2, if you want to act with E2 on this diagram, you just stack E2 diagram on top of this, and you just simplify it by the usual diagrammatical rules. So here you have a closed loop, you replace it by delta, and you propagate this line and this line. So you obtain this very naturally. For E2, you play the same. For this basis state, you can play the same game. You stack this diagram on top, and you obtain this basis state. And again, for E1, you stack it here, and here you have to propagate it like this to obtain 2. And you see you always remain in the same basis. So this is an important property of the standard models. If you have through lines, it's more complicated, but we're not going to need them here. Okay. So now we want to introduce boundary conditions into the system. So somehow in this system, the boundary conditions are trivial because the leftmost and rightmost line are not really distinguished. To deal with more general boundary condition, you extend this temporally algebra. So what you do first is you introduce an additional generator on the left. You call it BL, and it satisfies these algebraic rules. So it squares to itself, and if you sandwich it with E1, you get a weight YL, which is a new number we want to see. And then also this BL, it commutes with all the other generators. And so these abstract rules are actually very simple diagrammatically. So what this means is that if you represent BL by this diagram, which is actually called a blob in the literature because it has a blob. So it's these diagrammatical rules have the following meaning. So if you just multiply 2 blobs, so you have 2 big dots like here, you can fuse them into one and nothing happens. And this rule, it means that if you form a closed loop, but with a blob here, it has a different weight. So its weight is no longer delta, it's going to be YL. And that's how you modify your temporally algebra. So now you have different statistical weights for different loops, depending on whether they touch the boundary and carry this blob. Okay. And this defines something called the blob algebra because of this blob. Okay. So now you want to play the same game on the right boundary, okay, because we have 2 boundary system. So you introduce a blob BR, which you denote by a solid square like this. And then you make it satisfy the natural rules. but on the right this time. So if you fuse two of them, you obtain the dot itself, so nothing happens here. And if you sandwich it with the generator the last generator, so En minus 1, then you obtain a statistical weight YR. So it's different from Y left and from delta. And algebraically, this is expressed by the following rules. But really what's important is this diagrammatical interpretation. But this is not all, because now we also have another object. We can also form a closed loop which carries both blobs. So this one and this one. And that's why we have another statistical weight, capital Y, which is associated to a loop which contains both this blob and this blob. Okay. And now we have all the ingredients to build our two-boundary extension of the temporary leap algebra. And this is what's called the two-boundary temporary leap algebra, so not a very fancy name. And you see here it depends on 1, 2, 3, 4 parameters. So on delta, so the weight of a bulk loop, Y left and YR, which are the two weights on the left and on the right, and the capital Y parameter, which I just defined here. Okay. So now let me discuss the useful representations of this algebra. So they're very similar to the temporary leap algebra. The only thing we have to do is we have to take all the half diagrams I have shown you and we have to decorate them by blobs, so the solid objects like this, and also anti-blobs. So they're a whole object like this. And so these objects, why they're called anti-blobs is because if you multiply, for example, one whole square by one full square, you obtain 0, because BR squares to itself. And so the way you construct representation is just, well, you take the half diagrams I've shown you and you decorate them by these objects in all compatible ways, and then there are some action rules which are very natural from the diagrams I've shown you before. But the only object we will need, the only representation we will need is what I call the vacuum model, and denoted W, and it's a distinguished representation. It's of dimension 2 to the n, and it has no through lines. So basically you take the diagrams for temporary leap algebra and you decorate them by blobs and anti-blobs and you obtain this W. Okay, so it's not obvious at all that it's of dimension 2 to the n, so there's some combinatorics in there. I'm not going to show you, but if this can be proven. And also you see what's also very nice is that it's of dimension 2 to the n, and it's exactly the dimension of a Hilbert space. And this is actually not a coincidence, as I will show you in the next slide. But for the moment, let me just give you an example. So for two sides, you have only one diagram with no through lines, it's just a gap like this, and you have to decorate it by these objects in all possible ways, so you basically have only 4 options. You just take this, this, or this. And you obtain a space of dimension 4, which is 2 to the 2, so everything is compatible.
Does it mean the whole Hilbert space is just one representation?
Yes, this is what will happen eventually. But now I'm just defining an abstract diagrammatical algebra, but I'm just in one slide or two, I will show you how you relate it to the Hamiltonian, to the H and D.
Is this two-boundary temporary leap somehow a quotient of, I don't know, affine Hecke of type B, C, or something like this?
Well, yeah, there's some results like this. So there's a result like this definitely for the blob algebra, for the two-boundary algebra. Yes, I think so. So actually in the paper in which this algebra was introduced and studied systematically, it's a paper by Decomposition and Nichols, they actually use the Hecke algebra representation because somehow it helps them to derive the properties of this algebra. Okay. And so now the trick is the following. So you introduce this abstract Hamiltonian, capital H, with two coupling constants, mu left and mu right. And in the bulk, I just take the EI generators. And then there's a theorem by Decomposition and Nichols, so it's exactly the paper I just told you about. And so it's a quite technical theorem, but let me just state it like this. So there's some explicit mapping of parameters. So recall that the XXZ Hamiltonian, the non-diagonal XXZ Hamiltonian, depended on 7 parameters, Q and the boundary. So there's 7 parameters. And here in this object, there are 6 parameters. So there's delta, there's the weights on the left and on the right. There's the capital Y weight with so for a loop with two blobs, and also there are the coupling constant mu L and mu right. And there's an explicit mapping for these parameters. So you may wonder how can I transform 7 parameters into 6 parameters? But the reason is that actually in my non-diagonal XXZ model, I can always do a rotation in the XY plane and eliminate one of the parameters. So somehow here I fix a gauge in some sense. And the theorem is that this non-diagonal Hamiltonian it's exactly this abstract element evaluated in the vacuum representation of the two boundary temporal leap algebra. And you see it's compatible, because here is an operator acting on space of dimension 2 to the n, and here is also an operator acting on space of dimension 2 to the n. So there's a lot of things hidden in this theorem. So for example, this mapping of parameters, here you have to identify the Hilbert space of a spin chain with the link states I've shown you above, but this can all be done in principle. Okay. So this is the main first statement of the construction. And so the idea, if you want to study this Hamiltonian, is actually to study this abstract Hamiltonian, but you can do it in any representation you want. I mean, in any realization of this W representation. Okay, so the strategy is going to be to find a suitable realization of this vacuum module, and then to diagonalize H and D. So this trick will be used later on to formulate better ansatz. Okay, so now let me discuss this Uqsl2 invariant realization. So maybe before I do that, let me just give you a short summary, because there's a lot of Hamiltonians. So it's very clear. Let me just write that I have H and D, which is just H left, sigma left, plus H right, sigma right, plus the open XXZ Hamiltonian. Okay, and then I have this capital H Hamiltonian, which is minus mu L BL minus mu right B right minus sum over EIs for I and minus 1. And somehow these two Hamiltonians, they're equivalent if I take representation W of two boundary temporal leaps. Okay, so this belongs to two boundary temporal leaps. Okay. Okay, so let me just remind you what's the Uqsl2 algebra for those who may be not familiar with it. So it's an algebra generated by these generators, E, F, K, and K minus 1, and they satisfy these relations. One way to see this algebra is as a Q deformation of the Lie algebra of SL2. And the way to see it is take the limit Q to 1, and then if you rewrite this relation, you will obtain the enveloping algebra of SL2. And also you have to define this K as Q to the power H. So to obtain the SL2 triple EFH. Okay. And what about the representation of this algebra? So they are very similar to SL2. For example, if you want to define the spin 1/2 representation, you take these operators. So E just the raising operator, F is just the lowering operator, and K is just the exponential of sigma z, and it's written like this. And you can show very easily that it satisfies all these commutation rules. And this algebra actually it's similar to SL2, but there's one thing that is different, is how you define representation on tensor products. And for that you need a coproduct, which I'm not going to write here. And this is how you extend any action on any representation to a tensor product of representation. So for example, on C2 tensor n times, which is the Hilbert space we're interested in. But just to say that it's not an obvious construction. Okay. So in the XXZ spin chain, so as I told you, the SU2 symmetry is broken. So even with no fancy boundaries, just because of the anisotropy, the SU2 symmetry is broken. But actually, if you take the open Hamiltonian and you impose very specific boundary conditions, which are just written here, you obtain a Hamiltonian which is invariant under this action of Uqsl2, which I've shown you before. But for this, so this also looks like a non-diagonal XXZ Hamiltonian, but notice that here the boundary conditions are very specific, and if you do anything else, it will not be invariant under UQSL2 anymore. And also one important remark, usually in this Q-deformed settings, you take Q to be some root, like sometimes root of unity, but basically a complex number of module 1. So one thing to notice is that this term, it's imaginary, so these boundary conditions are actually imaginary. But this doesn't spoil the fact that the spectrum is mostly real, because you can notice that if you take the conjugate of this Hamiltonian, it just amounts to permuting the sides of your spin chain. So somehow you have a reality property which is still guaranteed by these boundary conditions.
And you can also choose Q to be real. Right?
Yes, you can also choose Q to be real, of course, yes. Yes. But I'm just saying that in most applications you choose it to be of module 1, but because somehow it corresponds to the critical case of a Hamiltonian, so that's why you make this choice usually. Yeah, but of course, if it's real, yeah, everything here is self-adjoint also. Okay. So this Hamiltonian, so the sum, this whole sum, and this boundary condition, they're invariant under UQSL2. But actually, if you just define the Hamiltonian densities here, which I've written here, so why these Hamiltonian densities is because since here you have a difference of sigma n and sigma 1, you can absorb it into a nearest neighbor term here, because they will all cancel out except the boundary terms. So you can rewrite this Hamiltonian in terms of this Hamiltonian densities. So you write it like this, you have like an irrelevant constant before. But the nice thing about it is that these Hamiltonian densities EI, they also commute with VQSL2. So not only the sum commutes with VQSL2, but actually each Hamiltonian density individually. So this is of course a very nice property, not only algebraically, but also because from a physics perspective, if you imagine now that you're considering a Hamiltonian with some impurities, or you change your Hamiltonian a bit, this property of commuting with QSL2, it will be preserved if you take different couplings here in front of the EIs. So somehow this Hamiltonian is kind of rigid to a number of deformations. Okay.
And this EIs also satisfies the temporally?
Yes, exactly. That's why I chose this notation, and it's the next point. These EIs will generate a representation of temporal algebra, and the loop weight delta is Q plus Q minus 1. It's actually it's quantum number 2, if you remember Jasper's talk. So it's the same Q basically. So it's a very natural parameter in all this business. Okay. But now. We want to study the two-boundary temporal leap algebra. Okay, so, and we also want to preserve this UQSL2 symmetry because somehow it's a very powerful object to work with. So the question is, can we find a UQSL2 invariant representation of a two-boundary temporal leap algebra? But there's a problem, is that the EIs, you can show, it's a theorem, it's a rather old theorem by Jimbo, I think, that the EIs, they already generate the full centralizer of UQSL2. Okay, so what that means is that if you want to, you cannot construct any other operator that will commute with QSL2. So every operator that you construct, you can express it as an algebraic combinations of the EI. So it will not be possible. So, well, what you do, you have to consider a bigger Hilbert space. So what you do is you take two irreps of UQSL2, which I'm going to later what this representation should be. And you consider a bigger Hilbert space, you tensor by XL on the left and by XR on the right. And then the space of intertwiners for UQSL2, it will be bigger. And this is why you may hope to find some operators B left and B right, which will represent the blobs of your two-boundary temporal leap algebra. And okay, and they also have to act on the two leftmost or the two rightmost sides so that they commute with all the other generators. And it turns out that the good choice for these XL and extract modules are Verma modules of UQSL2. So these are infinite dimensional representations of UQSL2. And what are these representations? Well, you take a weight alpha in C, and you just act on a basis, on an infinite basis like this. So you have this lowering operator, you have this raising operator, and the k's, they act diagonally on this basis. And if you're familiar with Verma modules for SL2, this is exactly the same representation, but only you have to replace usual numbers by Q-deformed numbers. But in the same, it's actually exactly the same representation. And also, of course, you have to exponentiate your H here. Okay, so it's a highest weight representation. It's just a generalization of spin J representation, but for complex spin J. Okay. And why these representations? It's because we satisfy simple fusion rules. So we want to define an intertwiner on the two leftmost sides. So, well, the easiest way to define an intertwiner is to decompose into irreducible representations. So this is what we do. We tensor with C2, and it turns out that it is expressed as a direct sum of V alpha plus 1 and V alpha minus 1. So it's actually the same thing as for spin J representation for J like larger than 0. Okay, and now you consider the Hilbert space I just suggested.
Sorry?
Yes?
So this is valid in the whole complex plane?
Oh no, you have some, no I didn't say that, but okay, you have some generality condition here. So you know that, for example, if alpha takes an integer value, it has a, you can quotient it and obtain spin J representation. So so alpha shouldn't be an integer, for example. Okay. Actually, this fusion rule will still be valid, but other things may become degenerate. So here in all this construction, I take alpha to be generic. But yes.
I was just talking about the fusion rule.
Yeah, the fusion rule. Okay, so it's
general.
Yeah, it's general except for V0, and if you take V0, you will obtain something called a tilting module. It's, like it's an extension of indecomposable representation. But I think for all alpha except 0, yeah, I think so. Except 0, this fusion rule will be valid.
Right.
I have to check it, well, but yeah. Okay, so now you take this Hilbert space, well, the easiest thing to do to define BL is to take the projector on either one of the factors. So, okay, we just choose to project on V alpha plus 1. And why take the projector? Because BL should square to itself, so it's natural to take a projector. And for B right, well, we take the projector on VR plus 1, acting on this tensor product. Okay. And now, well, you have to do a bit of computation, but you can show that these operators, they satisfy the following rules. And these are exactly the rules of two-boundary template algebra on the left and on the right. And the only thing you have to compute is these new weights, YL and Y right, and you can show that they are given by these expressions. So again, it's Q-deformed numbers, and you see it depends on the parameter alpha left and right.
Before you also had the capital Y parameter, is that?
Yeah, the capital Y, then I will talk about capital Y, because these are not the relation. The capital Y actually is where things gets really interesting. Okay, and so what about the weight capital Y? So it's the only remaining weight. Well, it turns out that it's, in this construction, it's not a number, but a central element of your QSL2. And this central element, you can compute it, and it has a rather simple expression. So what you do is you define a Q-deformed Casimir operator. So it's QSL2 has also a Casimir operator like SU2, which has this expression, and it commutes with the whole algebra UQSL2. Okay. And so obviously it will compute also with on any representation. Okay. So you evaluate this Casimir on your spin chain and you obtain some operator. And it will commute with the action of EI, BL, and B right. Okay? And also with UQSL2 since it's a central element. And then you can compute this weight capital Y to be this combination. Okay? So this may seem a bit magical, so how do you obtain this expression? So maybe those of you who are familiar with quantum topology, this Casimir C, you can express it as a loop going around the whole system. And when you express this in terms of your two-boundary template algebra, you can make the Casimir appear. Okay, so that's basically the idea behind this proof. And for this you have to use the diagrammatical calculus for intertwiners of UQSL2, but it's really manageable at the end. You obtain this simple expression. Okay. So then, okay, it's a central element. It commutes with all the objects we have defined so far. So it commutes with two-boundary template algebra. It commutes with UQSL2. So it's obviously a good idea to diagonalize it, because in any case it will define sectors on which you could restrict all the other operators. And in these sectors, this Y, it will take definite complex values. Okay. So to do so, we just have to diagonalize the Casimir, because all the other terms were just constants. And a way to diagnose the Casimir is again to decompose your Hilbert space into representation of Uqsl2, because the Casimir, it will take a constant value on each irreducible representation. It's the same thing as with a rotation group, the spin, the total spin, it takes a definite value on each irreducible representation. Okay, so let us decompose the Hilbert space into irreducible representations of Uqsl2. How do we do that? So we need just two elementary fusion rules. We need this fusion rule, so it's a fusion of two Verma modules, and it's given by this infinite sum. So, but it's discrete, so it's really manageable. And there's the rule I have shown you before. It's that if I fuse it with C2, you just decompose it into V alpha plus 1 and V alpha minus 1. Okay. And now you just apply these rules. It's a bit of computation, but it's really manageable. And at the end of the day, you obtain this decomposition. So you obtain only Verma modules with different weights, parameterized by some integer m here. And also these spaces, they appear with certain multiplicities. So I just entered by some multiplicity spaces, okay, here. And the dimension of these multiplicity spaces can be computed. And I have given it here. So for m between 0 and n, it's just given by a sum of binomials. And for m larger than n, it's just 2 to the n. Okay?
I'm confused. So how comes that you take tensor new alpha with a constant, right? C2 is a constant?
C2, C2 is a spin 1/2 representation.
Ah, I see.
Oh yeah, it's a C2 is spin 1/2 representation. Maybe I should pick a different notation. Yeah, and then yeah.
Because it looks somehow a bit strange.
Yeah, maybe it's not the best notation, but yeah, I agree. But
I mean, it might have been called V and W2 for them.
I will change notation for next time. Okay. So you obtain this multiplicity space as Zm, and you see there's something very nice happening is that for m larger than n, it has dimension 2 to the n, and this is the dimension of your Hilbert space. And this is not a coincidence. So now let me compute so the main motivation behind all that was to compute the spectrum of this y, which is an operator. And so the idea, okay, you see here, since these are multiplicity spaces, and since the Casimir, it takes constant values on this term, actually the weight y, it will take a constant value on these multiplicity spaces. So you can restrict it to these multiplicity spaces and it will be constant. Okay? So these are like the irreducible sectors of your model if you want. Okay, and how do you compute it? Well, you just compute the Casimir on a representation of V alpha. It's very easy to compute. You just plug in the highest weight vector and you obtain this value, and it's equal to this expression. And then you plug it into the expression for y, and you obtain this. So if you restrict y to this multiplicity space Zm, you obtain this combination of Q-deformed numbers, and I call this number Ym. So you see it contains, it depends on the sector you're considering. And that's really because this y, it's an operator, it's not a constant. So depending on the representation of Uqsl2 you will be looking at, it will take a different value. But now, if we restrict to the multiplicity space, well, we have a well-defined representation of a two-boundary algebra with weights delta, y left, y right, and ym. And you see in this algebra, the weight delta, you can pick it, it's a free parameter, it just depends on q. Y left, y right, they're also free parameters, they just depend on alpha left and alpha right. But actually this y, it's constrained. It's constrained because it's expressed in terms of all these parameters and of a discrete parameter m. So this ym is somehow quantized in this representation. You see? I cannot choose it as I want. I can just choose the sector and choose these discrete values. Okay, and now let me come to the theorem we have shown in our paper with Jesper, Azat, and Uqsl2. So if you denote Wm, the 2n-dimensional vacuum representation of this two-boundary temporal algebra, so the index m, it just stands for the fact that this capital Y, it depends on m, okay? But this is just the vacuum module I have shown you before. So the theorem is the following, is that for m between 0 and n-1, it's isomorphic to an irreducible subblock, dm-dimensional subblock of a vacuum module. So this is actually, this is normal because I have shown you the dimension in the slide before. You see this dimension. You see dm is, its dimension is lower than 2 to the m, so it cannot be the whole vacuum representation, obviously. Okay, so but actually it's a irreducible subblock of this Wm, and for m greater than n, it's just isomorphic to the vacuum module. Okay, so this is very nice because I've just shown you that we have constructed a Uqsl2 invariant representation of the vacuum module, and we know that it's related to the non-diagonal Hamiltonian. So now we have basically built a spectrally equivalent Hamiltonian, but with much nicer symmetry properties because it has this Uqsl2 symmetry. Okay. So now the consequence of all this is that if now you define H2B, so it has the same expression as this capital H Hamiltonian, but I consider it now as an operator acting on this big Hilbert space. Okay? And we denote the non-diagonal XXZ Hamiltonian like this. So this is the non-diagonal XXZ Hamiltonian, but with the value of a capital Y parameter equal to Ym. Well, then these Hamiltonians are related. So for m between 0 and n-1, this Hamiltonian restricted to this sector Zm, it will be a dm-dimensional subblock of a non-diagonal XXZ Hamiltonian. And for m greater than n, it will be actually equal to the non-diagonal XXZ Hamiltonian. Of course, in all these statements, there are like base changes between various representations, but the operators are exactly the same. Okay, so far, yeah.
This only works for these discrete values.
Yeah, it only works for discrete values of y. But actually, it's kind of a nice property because so probably it's here. So diagonalizing the non-diagonal XXZ Hamiltonian, actually, it's equivalent to diagonalizing this thing in a certain sector. Okay, and also, the important thing is that we can fix all the parameters except the capital Ym parameter, which is restricted to these discrete values. And they're fixed by the sectors of Zm of H2B. Okay? And actually, this quantization condition on Y is actually the Nepomniachtchi condition. Okay? So if you follow over a parameterization and you look at these values Ym, these are exactly the value that Nepomniachtchi found in this condition in which the Hamiltonian simplifies. Okay? And what we have just shown, I mean, by this construction, that is just a consequence of Uqsl2 fusion rules. Okay, so I don't think this was known before, and it's actually very nice that you can have an algebraic interpretation of this Nepomniachtchi condition, because usually in the before it just appeared from computation, just a simplification condition which appears from a computation, but here it has a very strong algebraic interpretation. Okay, but really the hard part is showing that. This Hamiltonian H2B, that its sectors are related to this vacuum model. This is a hard theorem which we managed to prove, but this is the place where all the technical details somehow are contained. Okay, because once you've done that, I mean, your life becomes great, because you can do just algebraic Bethe ansatz. Okay, so why can you do it? It's because for algebraic Bethe ansatz, you need what? You need a solution of a Yang-Baxter equation, so our matrix. You need a solution of a boundary Yang-Baxter equation, so a K matrix. So you just a reflection matrix to impose boundary condition. And you also need a reference state. And here in this Uqsl2 invariant realization, we have all these ingredients. And this is actually thanks to this symmetry. So first, the R matrix is constructed just from you just take the R matrix of Uqsl2. So you can construct it. I'll show you the expression later on. I mean, it's a known expression. But, actually, you don't even need K matrix because you see your spin chain is just XXZ spin chain in a more general representation. So if you want to build your monodromy, you just have to braid around the Verma module with the R matrix in a more general representation. You insert some indigeneity parameters, and then again you match it with your model. So basically, your K matrix, your reflection matrices are trivial.
Why is it so? I don't understand this.
I will show you later on.
Because that would be true if you were periodic, no? But it's not.
No, what I mean is that you have your representations here, and so you braid. So here's your boundary Verma module, and for K matrix you just braid around it with two R matrices. It's like, I think it's called the dressed K matrix.
No, but you should dress something.
Yeah, you're dressing trivial, you're dressing identity.
No, but that's a trivial K matrix.
It's a trivial K matrix, yes, but it's like, oh, you don't need a matrix, so you don't need to compute some fancy. Yes, but actually, of course, you need a K matrix.
Identity.
Okay, it's identity.
Matrix.
it's identity K matrix. Okay. And the reference state, well, you just take the highest weight state of your representation, because Verma modules are highest weight, C2 representations, spin half, one half representation are highest weight, so you just take this reference state. Okay, so to build your R matrix, you take the Uqsl2, the universal R matrix of Uqsl2, so not the affine, just the usual R matrix of Uqsl2, which has this expression, and you define these braiding operators, which you may know, so this is just intertwiners between representations of Uqsl2. Okay, and then you do the Baxterization trick to define the affine R matrices in any representation. So the Baxterization trick, it works only if one of the factors is C2s, but for X you can basically take more or less any representation of Uqsl2. So okay, you have to converge obviously, but here we only have highest weight representation, so we don't have this problem. Okay, and you take this combination.
10 minutes.
Yeah, I'm fine. It will be fine. Okay. And it satisfies the Young-Baxter equations as long as one of the factors is equal to C2. And this is sufficient to build the monodromy matrix. Okay. So the monodromy, so I don't know if you're familiar.
What do you get in this way? You get a standard R matrix.
Yeah, it's standard R matrix. Yeah, you just.
So why do you need all this if you could write down just the standard R matrix?
Oh, this is because I wanted to make a connection with Uqsl2 symmetry, and because I don't know. I mean, I'm used to the R matrix in C2 representation, but here I'm taking Verma modules, so it's just to show that it's.
No, if you take a universal R matrix and evaluate one representation as C2, it will be only two terms, yes?
Yes. Yeah. Yeah, you can also do the universal R matrix thing, but here it's... Okay, I may have skipped this part, but just to make it very explicit. Okay, so to build the monodromy, you just braid in one direction all your lattice and then you braid in the other direction with T hat, and then your transfer matrix is just will be the quantum trace of this whole object. So you need to take the quantum trace to guarantee the Qsl2 symmetry. It's just a Q deformation of the usual trace. Okay, and then you just derive it at a good point, and you obtain the two-boundary Hamiltonian I just defined it before. And actually, I have parameters zeta, L left and right here. These are related to the coupling constants. Okay, so now you do just algebraic Bethe ansatz. I mean, I don't need to recall how it works. You just act with the B operator, and you use the commutation relations to simplify, to compute the action of the transfer matrix on this vector. And then you compute the eigenvalues of A and D on the highest weight state. And what you obtain is that psi is an eigenvector with this energy as long as you have these Bethe ansatz equations. So this is just algebraic Bethe ansatz. There's nothing fancy about it. Adapted to the two-boundary case. And you see here, so for Temple-Ellipse case, so with no special boundaries, we wouldn't have had this factor. But now we have these boundary factors which implement the boundary condition. And they depend on the alpha, on the mu's, but you can also express them in terms of the homogeneity parameters. And these are very known equations which were derived by Nepomucci and a lot of people. But here we just derive algebraic Bethe ansatz. You don't need to do fusion or anything, you just apply the machinery. Okay. So these are precisely the Bethe ansatz equations under the Nepomucci constraint, as I told you. And also an interesting point is that M, it can be arbitrarily large. It's a Magnum number. Usually you're constrained because your Hilbert space is finite dimensional, but here is infinite dimensional and you can go as low as you want. I haven't done numerics for it, so I don't know if it's like physically justified to do this, but definitely algebraically you have a right to do this.
Yeah, but we don't really expect this from the XXZ point of view.
No, you don't. No, you really. Well, yeah, you don't expect it. Yes, but here in this construction, you can do. It will not be zero.
But they cannot correspond to the XXZ spectrum.
Actually, it does. It does. I mean, in the Nepomucci paper, he says that if you take M large enough, you will just change the value of capital Y. So this is kind of strange because the Magnum number, it somehow becomes a parameter, one of the three parameters of your model. But it's discrete.
What is the ground state? In which sector?
So the ground state is just all the highest weight state for Uqsl2 symmetry, so all arrows pointing up. And this is actually an eigenvector of this Hamiltonian. So you might ask, I mean, how is it possible?
Not the pseudo vacuum.
The pseudo vacuum, but. What's the vacuum, like the lowest energy? So from the one boundary case, you expect that you have to take m equals to n over 2. So it's in this sector, and then, well, it depends if you believe in all the properties
No,
of...
but, you know, the situation when your Magnum number is not bounded, well, you need to check where the energy doesn't go to minus infinity if you increase the Magnum number.
I think it depends. It depends on the choice of parameters. Actually.
I mean,
No, unless if you have antiferromagnetic state, it's not real.
But isn't it true if ym is fixed,
Yes.
then the Magnum number goes over a discrete range, right?
Yes.
If ym is fixed.
Yeah, ym is... Yeah, every time you diagonalize it in the sector, and each sector is finite dimensional, so the spectrum is...
So for fixed values, the parameters...
Yeah, to fix value of parameter, you need to fix a sector, and each sector is finite dimensional. So that's why...
M also the number of B operators?
Yes.
What he's saying is that for real ground state, so there is a sector for which, I mean, finite sector,
Yes.
which it is minimal, yes.
Yeah. Ah, you want to say like the vacuum of the whole Hamiltonian H2B? This one I don't know, but this one I don't know how it goes. But
we know the conformal spectrum, so we know what is the
Yes,
negative.
yeah, okay. Yes, I mean we have a conjecture for the conformal spectral of this model for various choices of parameters, and it should behave in a good way. So, again, you have to restrict some parameters, so you have to take Q to be module 1, etc., etc.
But when you change m, you change...
You change the value of a parameter.
ym, so you change your Hamiltonian.
Yeah, you change your Hamiltonian. That's why I only consider the problem in the sector, finite dimensional.
What does it mean that you diagonalize the Hamiltonian? Which Hamiltonian are you diagonalizing?
Well, either you diagonalize a block or you can diagonalize the whole H2B, but depends on the physical interpretation you want to put it. Okay. And so, okay, and also, yeah, we expected to provide an eigenbasis for H2B. So how much time are left?
4 minutes.
4 minutes, okay, that's fine. Okay, and so for the non-diagonal Hamiltonian, so just to finish with its relation, so because of the algebraic theorem I have proved, so basically you can interpret this Bethe ansatz equation as Bethe ansatz equation for this non-diagonal Hamiltonian. So for m greater than n, this is just exactly equal, but as I told you, for these values of m, it's just a subblock, but actually you can do a clever transformation using the representation theory template algebra to reach the other block. And actually, this transformation of parameters is written here. And in the end, you can diagonalize the whole range of non-diagonal XXZ Hamiltonian. And you can even reach negative values of m with this trick. Okay. Okay, so I don't have time to talk about the scaling limit, unfortunately, but we have conjectures from that. You can use thermodynamic Bethe ansatz. It's technical computation, but it's manageable. Okay. So let me just skip to the conclusion. Okay. So just a summary. So we started with the XXZ Hamiltonian with arbitrary boundary fields. Then we reinterpreted this Hamiltonian as a Hamiltonian in two-boundary temporally algebra, evaluated in the vacuum module W for certain choices, certain mapping of parameters. And then we constructed a different realization of the same vacuum module, but this time preserving Uqsl2 symmetry and identifying the different representation with sectors of this Hamiltonian. Okay, and then using that, we managed to diagonalize this Uqsl2 invariant Hamiltonian and thus the non-diagonal XXZ Hamiltonian, but with the value of one of the parameters discretized by this Nepomniachtchi condition. Okay, and so also we saw that this Nepomniachtchi condition, it has an interpretation in terms of Uqsl2 fusion rules. So, a few open questions. So the first natural question is, can you construct a spin chain covering all values of y? And we expect that to be possible, and but for that you would need somehow fusion rules with continuous decompositions. And for that, the natural conjecture is to take Q-deformed principal series representation of Uqsl2, which should have continuous decomposition, so you can have all the values of the y parameter. But this is very complicated. You don't have highest weight states. A lot of things changes. It's still work in progress. Okay, and I haven't talked about the CFT scaling limit, but we expect also this model to be related to fusion in some sense, because you have these two different boundaries and you fuse them, and maybe these partition functions can give you some information about the fusion of these fields. Okay, and then there's also questions about the QFT interpretation in terms of Coulomb gas, and finally some concrete problems in random geometry, in loop models, and ASAP, which are all very interesting if you know how to diagonalize this Hamiltonian and construct eigenstates. Well, thank you for your attention.
If not, okay.
Yeah, it's a question and a comment. So this highest weight was it the highest weight representation, this infinite dimension? So I have a paper some time back when I used fusion. I took the diagonal boundary K matrix and I fused an infinite dimensional both direction representation of Uqsl2, and I could by this way generate the non-diagonal boundary condition.
Okay.
I could show even that if I take this defect line and I move to the other non-diagonal boundary, then it can make it diagonal if this constraint is satisfied.
Yeah, okay, so here we have a similar thing happening. So, okay, you can use integrability to put the two boundaries on the same side and do algebraic decomposition. But really, I mean, the technical part about this, so I mean, it's really surprising that you can, if you just look at the K matrix at special vectors, that it takes this diagonal form if you pick a vector in a good way. And so I think you can observe it in this model too. But what's really complicated is to study the sectors and to actually see that you have all these vectors, what modules they correspond to. So to me, I mean, it's not sufficient just to say that if you at a vector, if the K matrix takes the same form, it's the same model, because you really have to study, I mean, what kind of vectors do you have in your model. So because, I mean, I'll show you the representation theory of two-boundary algebra, it's very rich, so you might have obtained something very different. It's not, I mean, to me, it's not obvious that you obtain the same states. And you see, also here you have to do something very non-trivial to reach all the eigenstates of a non-diagonal Hamiltonian. You have to apply an automorphism of a two-boundary Temple-Leap algebra to reach the other blocks. So there's something complicated happening here, and I don't know if you can just see it at the level of a K matrix.
I mean, by this transformation of putting one defect from one boundary to the other, you are making spectral equivalences. So I just showed that this. Okay, I will stop.
After. Well, let's speak anyway.